All right, as we continue on with triangles in Chapter 5, we've dealt with perpendicular bisectors. We've dealt with midpoints and mid-segments. And then we just got done talking about angle bisectors. The next thing we roll into are medians and altitudes. Now, a median is a segment from a vertex to the midpoint of the opposite side. It's similar to an angle bisector, except it doesn't necessarily bisect the angle. And what I mean by that is if we look at this triangle over here, if I bisect AC and label it F, that's a midpoint. We talked about that 2 sections ago. But then if I draw a line from B to F, that is a median. I can do the same thing with side BC. If I bisect it and label it E, that's a midpoint. Then if I draw a line from A to E, that is a median. The same thing with D. If I bisect side AB and label it D, I can then draw a median and call it CD. Now, just like the perpendicular bisectors, the angle bisectors connecting inside the circle. Remember, we talked about how the points of concurrency. Okay, that's a word that you've heard a lot this chapter. Concurrency is where those things intersect, and we can actually see that they intersect inside this circle at point P. Now, instead of it being called the concurrency point or the point of concurrency, this time we call it the centroid. And all that is the point of concurrency for the medians. That's all they are. Now, there's something very, very interesting about medians. And Theorem 5.8, and again, you don't necessarily need to remember that, but the concurrency of medians theorem, okay, the concurrency of medians theorem says that the medians of a triangle intersect at a point. We already know that. The point is 2/3 of the distance from each vertex. Let me say that again. The point is 2/3 of the distance from each vertex to the midpoint of the opposite side. Meaning, P is 2/3 of the way from B to F. P is 2/3 of the way from A to E. P is 2/3 of the way from C to D. And that's actually where we get these, we could actually take that information, that P is 2/3 of the way from each point, and we can actually write some statements about that. We can say that AP, let me clear this out so you can see it a little bit better. We can say that AP is 2/3 of the distance from A to E. We can write that as AP equals 2/3 AE. The same thing with BP. BP equals 2/3 of BF. We can see that. And then the same thing can be true with CP. And that's where we get these 3 statements right here. That this point, this centroid, is 2/3 of the way on the median. Now, here's a little note. Using a different fraction other than 2/3, what is another way you could represent all the medians inside the triangle? And if so, what fraction would you use? Well, there's a fraction similar to 2/3 that we could use. Instead of talking about these distances, what if we started talking about these distances? We wouldn't be talking about 2/3 anymore. Do you know what fraction we'd be talking about? We'd be talking about 1/3. And let me show you what I mean. If I take one of the medians, like AP, if that represents 2/3 of the way, how much is left? And the answer is 1/3. There is 1/3 left, and it involves this segment right here, or PE. So I could say that PE equals or represents 1/3 of AE. This small section represents 1/3 of the whole. Just like this section, or AP, we can see it right here, it represents 2/3 of the whole. Which makes sense. If AP is 2/3, then PE would be 1/3. And we can use that same idea to write similar statements about PD and about PF. PD would be 1/3 of CD, and PF would be 1/3 of BF. Now those are 3 more statements that you can make based on the 3 statements they made using the medians. Now sometimes they might give you, in a math problem, they might give you this distance, and then you need to figure out the rest. Or they might give you this distance, and you need to figure out the rest. So really it just depends on what they give you, but you need to know that there are 6 different statements you can make. 3 of them using 2/3, 3 of them using 1/3. Let's practice that a couple times. In example 1, we're given triangle RST. I'm told that Q is the centroid. And I'm also told that SQ equals 8. Then they tell me to find QW and SW. I'm told to find this distance, and I'm told to find this distance. Now, in order to find those 2 different things, I need to write 2 different statements. I need to find a statement that I can use to find QW. Then I need to find a statement I can make to write SW. Now, right away I can see that SW is the whole thing. SW is made up of SQ plus QW. That's not too tough. Let me erase some of this so you can see. I'm going to use the segment addition postulate, the segment addition postulate, the segment addition postulate to say that this segment plus this segment equals this segment. The 2 smaller parts make up the whole. SQ plus QW equals SW. That's just the segment addition postulate. But for QW, I need to look back at my theorem. QW is the smaller of the 2. Wouldn't you agree? We can say, because we know that this point is the centroid, we could write that SQ is 2/3 of SW. I can look back at my theorem, and each one of these segments, excuse me, each one of these segments from the vertex to the centroid is 2/3 of the whole. From the vertex to the centroid is 2/3 of the whole for all 3. So I can take that and apply it. From the vertex to the centroid equals 2/3 of the whole. Well, I know that SQ is 8. So I can substitute it in here and say, instead of writing SQ equals 2/3 of SW, I can say that 8 equals 2/3 of SW. Now this problem, we're going to rewrite right here. Get rid of this guy because we don't need him anymore. We were told that SQ equals 2/3 of SW. We've substituted 8 for SQ because we know that SQ equals 8. And we just drop down everything else that we didn't use. Now I can use my algebra to solve for this. And I'd find out what SW is. Now, how do I get rid of this fraction? You know how to get rid of a multiplication problem. You know how to get rid of a division problem. How do I get rid of a fraction? Well, I have to multiply it by its reciprocal. Remember, a reciprocal is a fraction flipped over. And I want you to watch something. If I take 2/3 and multiply it by its reciprocal, which is 3/2, look at what happens. The 3's cancel, the 2's cancel, and I'm left just with SW. But I multiplied this side by 3/2, I need to multiply the other side by 3/2. Remember that when we multiply in a fraction, we multiply straight across, and we just leave it as a fraction, leave the denominator down there. 8 times 3 is 24, and I leave the 2 in the denominator. But I can reduce this because 24 divided by 2 is 12. And I solved for SW. Now, if I go back to my notes, I solved SW. I don't need this. It was fun making it, but I found out that SW is 12. But now I need to find QW. Well, there's two different ways you can do it. We can take the segment, or we can take the theorem that we found right here, that SW equals SQ plus QW. And if we substitute everything in, if we substitute SQ as 8 and QW as 12, or excuse me, SW as 12, we have a simple problem here that will help us solve for QW. 12 equals 8 plus QW. If I subtract both sides by 8, or if I subtract 8 from both sides, I'll find out what QW is. 12 minus 8 is 4. QW equals 4. Using the concurrency of medians theorem helped me find SW. Using the segment addition postulate, I found out what QW was. Now those are medians. And a median, remember, is a segment going from a vertex to the midpoint of the opposite side. And from that, we get all these different identities. Some of them with 2/3, some of them with 1/3. Then, the next thing we're going to talk about are altitudes. Now, an altitude is a perpendicular segment from a vertex to the opposite side, or to a line that contains the opposite side. And let me show you what that's saying. I'm going to draw a triangle. And what I'm going to do is I'm going to put a point on each corner, or each vertex, if you will. And what I want to do is I want to draw a perpendicular line from this point to its opposite side. A perpendicular line, meaning when those two lines intersect, they should form a 90-degree angle. Now that's not too tough, that makes sense. Now I'm going to do it with this point. I'm going to draw a perpendicular line from the point, or from the vertex, to the opposite side. Then I'm going to do the same thing with this point. And just like the angle bisectors, just like the perpendicular bisectors, just like the medians, what do you notice? Exactly. They have a point of concurrency. The lines containing the altitude of a triangle are concurrent, meaning they'll meet at a point. Now, what I want you to notice is that sometimes, just like perpendicular bisectors and the angle bisectors, the altitudes of a triangle can be concurrent, meaning they meet at a point. Their point of concurrency is called the orthocenter. A lot of weird words for these points of concurrency. We just had the centroid with the medians. Now we have the orthocenter. And similar to the point of concurrency for perpendicular bisectors, the location of the orthocenter depends on what type of triangle it is. For example, in an acute triangle, the point of concurrency, the orthocenter, is inside the triangle. If you have a right triangle, it's on the triangle. The orthocenter is on the triangle. And in an obtuse triangle, the orthocenter is outside the triangle. Now I'm going to go back in my notes to the perpendicular bisectors of a triangle, and we're going to see how they compare. Let's go all the way back to our perpendicular bisectors. Oh, we went too far. Now we got to hit fast forward. Okay. This is dealing with our, where are we at? This is dealing with our perpendicular bisectors. And in an acute triangle, it's inside the triangle. In a right triangle, it's on the triangle. And obtuse is outside. So we go inside, on, outside. Inside, on, outside. Just like the perpendicular bisectors. If it's acute, both of them are inside. If it's right, both of them were on the perpendicular bisectors and the altitudes. If it's obtuse, both the altitudes and the perpendicular bisectors meet at a point outside the triangle. Now, here's a quick question. Why would you need a point of concurrency for altitudes? What purpose would this serve? And the answer to that is in construction. Those points, or that point, is so strong when you're dealing with construction. Let me show you something. Let me get a triangle up here. And let's actually get a couple. There's one, and there's one. And those are three different types. But now let's draw a couple altitudes real quick. This altitude from this point to the opposite side is actually going to be over here. Let's draw that, because that line is going to extend up. This line is going to extend over, and actually, if we extend this side out, this perpendicular bisector is going to be right there. That point is the point of greatest strength. Meaning if you have weight coming down on that point, that triangle will be able to support all that weight. The same thing could be said for a triangle like this. Here's the point of concurrency for a altitude. That point, okay, if you have weight coming down, and that point is attached to the parts of the triangle, it can hold all of the weight, just like up here. If I have this point connected to the sides and the top, then whatever is in this triangle, let's say there's a truck in the triangle, okay? Maybe this is a weight going across the bridge. So let's draw a truck. Kind of looks like a dog with wheels. But this point can support all the weight of that triangle, even though it's above the triangle, just like right here. I can put whatever I want inside this triangle, and the strongest point is going to be that point right there. And so we use that idea of an altitude in construction. Now let's actually try and find some information. In example 2, we're given triangle ABC, where G is the centroid. So we're dealing with medians again. Remember, centroid means median. We're told to find the length of the following segments if BG is 6, if AF is 12, and if AE is 15, meaning the entire length from A to E is 15. So we're told to find some stuff. We're told to find FC, first of all. Let's look at what FC is. FC is a line segment going from F to C along AC. But think about this. What is point F? Dealing with medians. Let's go back so you can kind of have a refresher. When you're dealing with medians, what do the letters on the sides of the triangle represent? They represent midpoints. So if I go back to my problem, all of these points on the sides of my triangle represent midpoints, meaning they bisect the sides into two equal parts. Well, if I'm looking for FC, what is something that I could use to find FC? Is there another length that I could use, or is there another segment I could compare it to? And the answer is yes. FC and AF are the exact same length. Point F bisects AC into two equal halves. This is 1/2, this is 1/2, meaning that they are congruent sizes. So when they told me at the beginning that AF is 12, that tells me right away that FC also is 12, because they have to be congruent. So there's one of the problems. If I keep going, let's look at number 2. They want me to find the length of AG. Well, what do I know about AG? Without knowing any numbers, is there an equation or a problem I can write down that compares AG to the rest of the part? Yeah. AG, based on my median, AG, or from the vertex to the centroid, is 2/3 of the whole. Going from this vertex to the centroid represents 2/3 of the whole. So I can say that AG is 2/3 of AE. Now they told me something up here. Right when I started, they told me that AE was 15. So I can substitute 15 in for AE and actually find what AG is. Remember that when you multiply in a fraction, you multiply straight across and you leave the denominator. Well, 2 times 15 is 30, and we just leave 3 in the denominator. But then you can simplify that. 30 divided by 3 is 10, which means that AG is 10. Now let's look at BF. BF represents a complete median, cutting across the entire inside of a triangle. So let's set up a equation that uses BF. What do you think? There are actually 2 of them. And I think we erased. Yeah. Here's 3 of them, and then we wrote 3 more that dealt with 1/3. But we can use that information about the 2/3 to help us solve this. What part of BF is 2/3 of the whole? Remember, it's from the vertex to the centroid, or from the vertex to the center. So BG is 2/3 of BF. From this point to this point is 2/3 of the whole. So BG equals 2/3 of BF. But they actually told me that BG is 6. So I can substitute 6 in here, write down everything else because I didn't use it. And now here's a math problem that I can use algebra to solve. Now, it's kind of tough to get BF by itself, but I showed you how to get rid of a fraction like that. Do you remember? I hope that you're saying to yourself, you multiply by the reciprocal. The reciprocal of 2/3 is 3/2. Remember, we just flip the fraction over. But what we do to one side, we have to do to the other, so we have to multiply both sides by 3/2. When I do that, look at what happens. The 3's cancel, the 2's cancel, and I'm left with just BF by itself, which is what I want. I want to know what BF is, so I need it by itself. Here, we can multiply straight across and leave it as a fraction. 6 times 3 is 18, divided by 2. Now I can simplify this and say that BF equals 18 divided by 2, which is 9. Now, the last part that I have to use, or that I have to solve, is GE, which is right here. Now, I've already been told that AE is 15, so the whole thing represents 15. And I actually already found AG. I found out AG was 10. So to find GE, I could use the 1/3 that I was talking about earlier, or I could use the segment addition postulate. Really, whichever one you want. Both of them will work. The first thing I'm going to do is write a segment addition that compares AG and GE. Well, AE, which is the whole thing, is made up of, or equals, AG plus GE. That makes sense. Using the segment addition postulate, I know that going from A to G and from G to E will get me the entire length of AE. Now I can substitute some values in. They told me at the beginning that AE was 15, so I'll substitute 15 in. I solved AG to be 10, so I'll substitute that in. And the only thing I have left is GE. Now, if I use subtraction, I can solve for GE. When you subtract 10 from both sides, the 10's cancel out on this side. You drop down GE because you didn't do anything with it. And you find that GE equals 15 minus 10. Well, you know 15 minus 10 is 5. So we solved GE to be 5. Not too tough. Those all dealt with medians, by the way. Let's keep going. And now we're going to look at your homework where you're not only going to solve for medians, but you're going to solve for altitudes. Let's go ahead and do that now.